Welcome to the second session of the Computational Challenge. This is a series of talks given by Dr. Andrew French, and you can ask questions via the Q&A. So please type in there. We've got a few of us ready to type answers out. Try and keep the questions to be useful ones. This session is being recorded, and it will go on the BPHO website, where you will also find last week's session recording. So please don't ask that. The competition details will come out in April, or a little bit before, in fact. It's not due until mid-August, and it gets marked by early September. So that should cover about half the questions that get asked. So, but do feel free to ask other ones. And I hope you have a good session. So what you should be doing is writing down notes on paper. Even though it's a computational course, you need to write things on paper. Otherwise, you think, oh, that's an interesting idea, and then you forget about it later. So notes are to be made. You can't sort of do the typing of the sort of the code whilst it's being talked about. The talk is to give you ideas and suggestions for what you might do. And there are follow-up exercises in the materials that you can download either from the Eclecticon website or from the BPHO website. There are zip files there, and you will find the contents of the various codes are available and ideas for you to follow up with. Okay, so thank you very much, Dr. French.
Okay, good evening, everybody. So the final frontier. We're going to do some astrophysics today. We're going to look at models of orbits, of stars, planets, and their motion, all that kind of thing. So this actually follows on very much from last year's challenge. In fact, some of the slides, you might see the sort of garish yellow boxes from the challenge notes. So if you did the challenge last year, you might see some things that you might have a go at, but there are lots of other things too. And if you are a newbie, congratulations, well done. It's very nice to see you. This will also going to be a hint of the kind of stuff that will be in this year's challenge, although that will be, the content will be released, it's all top secret, will be released just before Easter. So I'm going to go and share my screen. So if I could just confirm, Nina, can you tell me, can you see this all right? Is this coming across all right?
Yes.
Yes, yep.
Fantastic. Right, so gravity and astrophysics. This is session number 2. Welcome to the Computational Challenge, everybody. Right, so firstly, we're going to talk a few sort of notes. So some of you may know this very well, others that might be brand new, so I will sort of pitch that in the middle. So let's start off with Isaac Newton, 1642 to 1727, thereabouts. So this is about going from the ideas of Johannes Kepler, who's this chap with this amazing sort of orbital ruff that he's wearing. You know, I don't know if that represents a sort of interesting sort of looping orbit around his neck, but an amazing tour de force on the data of Tycho Brahe, the 3 laws of Kepler of orbital motion, which then were extrapolated and expanded upon the mathematical language that Isaac Newton developed. And pretty much that's the kind of stuff that, although that, you know, we will write it in a different way, that we still use now. Unless we're talking kind of quite more extreme gravity systems where we do need something like general relativity, the theories of Newton actually will predict the motions of the planets pretty accurately. We can send people to the moon just using Newtonian dynamics. So this isn't just history. This is actually really useful stuff. All right. So as you can see in the picture, I've got a sort of simulation of the solar system. These are sort of all the planets. To scale. Notice Pluto looks kind of strange. That's because Pluto is actually tilted from the plane of the ecliptic. So we'll see a sort of 3-dimensional version of it later. So what's the kind of key idea? Well, if we have a look at the picture in the bottom, we've got, this is a sort of red giant star. It's a sort of red star here at the focus of an ellipse. So Kepler's first law says that the orbits of one planet about a star, or in fact, 2 bodies about their common center of mass, are ellipses. So circles are special cases, and the one of them, the center of mass is at the one of the foci of that ellipse. So in the case of a star and a planet, the mass of the star is so much greater than the planet. Essentially, the star is not going to move very much, and the star is going to be the focus, or one of the foci of the ellipse. So some geometry here. We've got a polar geometry, range r and theta, okay, which is the polar angle measured sort of are anti-clockwise from the horizontal. And that's sometimes a better way of describing sort of circular motion. But we've also got our Cartesian XY axis here in astronomical units. So one astronomical unit is basically the average distance between the Earth and the Sun. All right, so that's a sensible scale for solar systems. So what's driving this? Well, there's basically only one force, and that is gravity. And gravity is acting between the centre of masses. And Newton's law of gravity basically says that it's proportional to the sort of the product of their masses. So you get a bigger mass of the star, you get a stronger force of gravity, and inversely proportional to the square of the distance between them. So gmm over r squared is that force in newtons, and g, the universal gravitational constant, is what turns mass and distance into a force in newtons. All right, and that's thought to be a universal constant of the universe, right? Hence the name. So what else we got? Well, we've got some definitions. So the semi-major axis, that's the distance, the sort of long axis of the ellipse, and the semi-minor axis is the short axis of the ellipse. And so A and B are half those distances respectively. So what we can do is we can define an ellipse in polar coordinates and then convert those to Cartesians. And that's sort of one of the problems that you want to do, all right, in terms of plotting your orbits. So there's some really nice bit of maths in this. So the range in general for an ellipse has a sort of cosine kind of form, and the cosine appears downstairs. So we've got A, which is my semi-major axis. So that's obviously bigger when that's larger. And epsilon is something called the eccentricity of the ellipse. I mean, this is all great stuff. The language, that goes back centuries is really exotic, I think. So an eccentric ellipse is when epsilon is bigger than 0. All right, which means you get a more squished, pronounced eccentricity. So if you think about it, if it's a circle, B and A are the same. So we've got 1 minus 1, and that's going to be an eccentricity of 0. So an eccentric ellipse is, or an eccentric circle, if you like, is an ellipse. And then lastly, we've got Kepler's third law, which says the square on the period is proportional to the cube of the semi-major axis. All right, and it also involves pi, g, and the masses as well. And in most cases, the little m here is negligible compared to the mass of the star until we've got a binary system. So that's the kind of core stuff of which we can make some recipes. So we mentioned Kepler's 3 laws. So let's just summarize these. By the way, just to go on from in terms of resources, etc. So all of these slides are available from the BFO website. And if I just come out of this slightly, so I think at the moment, see what you can do, write down some notes about some of the key ideas, basically what you think is interesting. And we're going to talk very shortly about some projects that might come out of this. And they're kind of, I think the best way of engaging with this stuff is go, oh, that's an interesting model. I think I might have the skills to do that. And then have a go, download the details, follow the instructions, write some code, write some Excel, do some Excel, that kind of thing, and then have a go. I think that's going to be much more useful than trying to sort of scrab down some text. So this is all downloadable. And if I just drag, so this is my website, the Eclecticon. All right, which Nina, if you could put that in the chat, that'd be amazing. And then if you basically click on, say, physics, for example, you can go to the British Physics Olympiad page, and you'll get the computational challenge, which will go here. So if you click on this link, Gravity and Astrophysics, you'll get to the presentation that I'm talking about. And any of the MATLAB code, you can just download by clicking on these icons here. And in fact, any of the other sessions that we do, you can get from this. And there's a book which goes with it, which is this book I published a few years called Science by Simulation. So that's how you get to it. And the BFO page, you can link from this. And there's a computational challenge page, which kind of has similar materials, including a recording of last week. Right. So if you've got any questions about access, do please put that in the chat. So let's just go back to our full screen. I'll also pause a little while. So if you do have a burning question, stick it in the chat. And unless it's particularly, I do sometimes get interrupted. That's fine. Otherwise, I'll pause every few minutes and we'll have a roundup of the questions. Right. So Kepler's 3 laws. Well, the first one is that the orbits are ellipses with, well, we'll talk about the sun for our solar system, but we could have any star. All right. Our solar system is a pretty average one that contains this jewel, which is the Earth. But there are billions of solar systems in our galaxy, and there are billions of galaxies. All right. So that's the ellipse, are these sort of binary systems. So now here's Kepler-2, which is illustrated by this picture, and I programmatically created this. So that would be a nice project. So in a given time, I think this might be a year or something like this, the area swept by a planet. So for example, where my sort of cursor is at the moment, going from there to there, that might represent a year of motion, right? If you draw a sort of arc, a sort of sector rather, between these points and color it, that area swept is going to be the same in equal times anywhere around this elliptical orbit. So when we go a bit closer to the star, you'll notice it's going faster. So the sort of arc of the area is going to be much larger, but obviously it's closer. So the total shaded area is going to be, it's going to sort of have a larger arc, but the radius is going to be smaller. Those areas are equal. So equal areas are swept out in equal times. And then lastly is the third law, which a lot of you who've been doing some astrophysics in your A-levels will be using. The period squared goes as the cube of the semi-major axis. Although if it's circular orbit, that's just the radius. Okay, and in fact, if you work through the kind of calculus of this, there's actually a formula for the rate of area swept. And if you have kind of eyeball this, you'll notice that's a constant for our elliptical orbit. There's nothing here, it varies with time. Right, so that's the sort of thing. And actually, this is a recipe. You could put those into MATLAB or Excel, and you could say for any kind of eccentricity or semi-major axis, plot me this orbit. All right, and so this is what I've done. That's an input. M is 2 solar masses. That's the unit I've used. I've defined the eccentricity. It's worked out the period in years and put that in the title, and then drawn me this rather nice diagram. Okay, so that'd be quite a nice thing to do. So that could be project number 1. All right, so a little bit more sort of theory. Now, this some of you may have. I like to introduce gravity for sixth form. I do this tends to be my upper sixth. This is how I do it, and I sort of borrowed this from one of my colleagues, Dr. Klern, who's also got a great book, sort of about the language of physics at my school at Winchester College. And so this is kind of how I guess we introduce this. So the idea is to ask, well, how far will the moon fall in 1 second? All right, so I'll sort of walk you around this. Now I've got a very much not to scale picture. And we'll have to think about, well, what would Newton have kind of known at the time, right? So this is sort of pre-Newton. What we're trying to do is justify that inverse square law. So this law here of Newton, that the force goes as 1 over r squared. So how might we look at this? Well, so we'll go back to what the Greeks knew and, what's been known since antiquity. So let's assume it makes sense for a moon to go in a circular orbit. Okay, we kind of see the moon rise and fall. That's not an entirely crazy stretch of the imagination. And since sort of ancient times, I think this has been done by shadows, that kind of thing. But there might even be an Olympiad problem that has talked about this. Perhaps Mr. Hughes and Professor Chung, you can mention if there's a link here. But about 60 Earth radii is the distance between the Earth and the Moon, roughly speaking. The Moon is not really executing a circular orbit, but it's not far off. So you could ask, well, how far does it fall in 1 second? Well, it's going to be that distance, delta, that I've got written here. All right. So I've drawn a right-angled triangle to describe the motion of the moon. So immediately I can do a bit of Pythagoras. So I'll you can work through every step, but if you look at the top, we've just looked at the sides of the triangle. And I've used that to work out an approximation for how far it falls in terms of d, the sort of distance, which is fairly close to the arc distance, because remember, this angle will be really tiny in 1 second. All right. So d is pretty much the arc length rather than just the sort of horizontal distance, and involving the Earth. The 120 comes because of the 60 r Earth. So the moon distance is about 60 Earth radii. So in 1 second, we can actually work that out. How far will it travel? Well, in terms of the arc, we can think about what fraction of 2 pi r, so 2 pi times 60 r Earth, that's the total circumference. So basically, what will it do in 1 second? So we can divide that by how long it takes to orbit the Earth. Let's just say that's 28 days. So if we work out the circumference of the moon's orbit about the Earth, which is the one on the top, divide it by the amount of time it takes, we have about 993 meters per second. Let's call it a kilometer a second, something like that. All right, about a 30th of the orbital speed of the Earth around the sun. So let's put these things together. So if we know d is this, that's just by observing the moon. We've just got Pythagoras from our circular orbit and the distance between the Earth and the moon. Put that together and we can estimate what delta is. And if you put in the numbers, it's about 1.3 millimeters. So in 1 second, the moon falls, in a sense, about a millimeter. Now, what else do we know at the time? Well, we know Galilean physics, right? So half AT squared is how far something moves in a constant constant acceleration motion, right? If you start from rest. So if you can kind of think about that radial infall being as a result of an acceleration, which I think, over a second, I think we can do that. It hasn't really changed its distance by appreciably. So I think that's not a bad model. And we use that on Earth, all right? Well, given, if we sort of say that, let's estimate an inverse square law. So let's just say the gravity of the moon is 160 squared, all right, 3,600th of the gravity at the surface of the Earth. Why is that? Well, because it's 60 Earth radii away. Then you stick in the numbers, and guess what? You get 1.3 millimeters. So that kind of, it doesn't prove, I think it can't really prove anything in physics, but it doesn't really sort of derive, but it sort of said that we're onto something here. We can show, independent of this, the thing I've got above the dashed line is nothing to do with Newton's law of gravity. So independently, using Galileo's principle, the sort of half AT squared, and Newton's law of gravity, we get the same answer. So I'm not really sure if actually Newton did it this way, but it's a nice way of introducing why an inverse square law might work. So before we move on, are there any questions that have come out of that into the chat? Nope. Right, excellent. So there we go. We've got some good facts here for the physics pub quiz. How far does the moon fall? And how far does the moon fall in a second? It's about a millimeter. Right. So here's a nice little model as well. So, and this is another thing you might wish to plot. We've got this inverse square law of the strength of gravity. So not the force on a mass that's orbiting, but the force per unit mass. We call that G. All right. So that would be 9.81, all right, at the surface of the Earth, for example. So that's an inverse square law. We can see that graph plotted. All right. So what I've defined X here to be the radius divided by the radius of my planet. So it doesn't really matter what my planet radius is. I've got a sort of dimensionless scale. And that's a really nice little tip in terms of when we talk about computational physics. Really, we're not talking about as a separate subject, but how can we use computer tools to make our life better and make our physics more clear and our calculations easier to do. So things like using dimensionless variables is a really good idea. All right, it generalizes our problems. In fluid dynamics, that's absolutely the core of what you do. So as a nice habit, when you're making models, which is essentially what we're doing, get into the habit of making things dimensionless. This is whatever big R is, like the radius of the Earth, for example, that scales our model. All right, and we're doing in terms of G at the surface of our planet. So for example, if we're doing it relative to Earth, that would be relative to 9.81 newtons per kilogram. If it was another planet, then Jupiter, that would be a bit higher. Now, interestingly, as we go inside a planet, now this assumes that we've got constant density. Not quite true in the Earth, and certainly not true when you go into something like Saturn or Jupiter, a gas giant. However, if you can accept that as a sort of basic model, what's rather interesting is that the strength of gravity is the same. The sort of shell on the outside all cancels out. All right, that's called Newton's shell theorem. All right, which is basically why inside, if you apply the same ideas to electromagnetism, which we'll look at in a few weeks' time, that's why there is no electric field inside a spherical conductor. It explains how a Faraday cage works. It works the same for gravity. So basically, the only thing that matters is the sort of mass within this. If you can sort of imagine drawing a circle within this sort of planet at radius little r, all right, only the mass within that sphere is what matters. So because m goes as 4/3 pi r cubed, all right, times the density, there we go, you stick that into this formula and you end up with a linear variation with range. Now, here's a question, all right, if our acceleration is proportional to distance, and I drill a hole through a planet, all right, what kind of motion is there where acceleration is proportional to how far away you are from the centre? Can you put your answers in the chat, please? Right, what do we got?
I'm still waiting.
Oh, don't be shy. Right. Okay. Whoa, we foxed you. So, okay, here's the answer. So, rather than going for the Earth, all right, we're going to go for Cybertron. So, when I was growing up, it was all about Transformers, robots in disguise in the 1980s. These days, it's a Michael Bay, a flashy film. Those days, it was these things made of metal and plastic that, you know, were a triumph of engineering. All right. So the Decepticons and the Autobots are from Cybertron, this planet made of metal. So I'm going to make a bold assumption that this is a uniform density, and maybe we can make it made of titanium. All right. So here we go. Here's my Cybertron metal planet. Now, obviously, in Cybertron, the Autobots and Decepticons have go all the way down, and they've turned this into a habitable sort of metal world. So I'm sure that they will have a really efficient transportation system. So the idea is you drill the hole diametrically in this planet. And so let's drop a kind of mass down this shaft. So mass M is that's the lift. All right. So you drop a lift from rest at the top, and what's going to happen to it? Well, there's going to be some force. There's going to be weight, right? But how is that weight going to change? Well, we've already mentioned, all right, that it basically depends linearly with distance. And so if you work it through, so let's just explain the notation if you're not used to this. So mass times acceleration is vector sum of force. That's Newton's second law. X double dot means acceleration, the rate of change of x here. So the second derivative if you've done some calculus. And so there's our gm, there's my x squared. X is the distance in this case. So if you put that together, you've got the acceleration is minus 4/3 pi g rho, the density of my titanium world, times the distance from the center. And that is an equation of simple harmonic motion, which looks like this. If you have a pendulum swinging or a mass on a spring, oscillatory motion. So formulas of this form, a cosine wave, for example. So x starts at r, the radius of my planet, and it varies cosinusoidally as it oscillates around. So what's the period? Well, if we compare the 2 pi over p all squared, if you differentiate that bit twice, you'll get this equation here. If we compare this bit with what I've got here, then you can work out what the period is. It's root 3 pi over g rho. Now, this is brilliant. It doesn't involve anything to do with the radius. So as long as the density is constant, then it will take the same time to go there and back, regardless of the radius of your planet. So if you had a kind of mega Cybertron, all right, maybe the Decepticons have left and decided to make an even bigger Cybertron made out of titanium, the time it takes to go on their diametric lift will be exactly the same. Or if you made a mini Cybertron, a kind of Cybertron moon, that would also take the same time. So here we go. So this is the difference between a titanium planet of average density, density 4,510 kilograms per cubic meter. So the Cybertron would take 93 minutes. And on Earth, it's a slightly larger average density, the iron we've got. It's about 5,513. And this produces a rather pleasing result. And any one of my students on this call will know that 42 is the sort of magic number from Hitchhiker's Guide to the Galaxy. Well, that's the time it takes to go from one end to the other. So twice that, giving you 84, is the there and back time. So done a bit of maths. What can we do for a simulation? Well, let's put this all together, shall we? So I'm going to come out of this. And I'm going to go into MATLAB, my sort of choice of coding. To be honest, if you're new to coding, it doesn't really matter what you start with, as long as you're happy, you like the language, you understand how it works. So most people either start with Python because it's free, and then sort of download various things like matplotlib, etc., or NumPy to do some things. MATLAB isn't free, but it kind of works out of the tin. So you can have your argument with yourself whether you want to go free open source or pay for a product. Either any of those things work beautifully, and there are probably hundreds of other languages too. So before I talk about through how this is all working, let's just run it. So I'm going to run this bit of code, and hopefully you can see a lurid green planet. All right, this is a high quality animation. And so we've got something going around in circular motion, uniform circular motion of period 84.4 minutes. And that will line up with my oscillation, which is this going on this diametric lift system. So it's going fastest in the middle and goes to 0 speed at the top. So that's really good. But there was a film called The Core, I think, with Colin Farrell in it. And if you like your sci-fi, and I think that uses that as a sort of narrative device. So just to peer inside that code. This is
one of the very worst movies ever.
Oh, I think we could probably have a long conversation of what's even worse than that. But there we are.
Well, Moonfall is even worse. The physics behind Moonfall is even worse.
Indeed. Yes. So what have I done? Well, basically, there's lots of green stuff. That is a commentary. That's the most important stuff in your code. That explains to you what you're going to do. So I always write that first. And then I've got a thing called function gravity clock. So basically anything within this is kept within memory of my my bit of code. I can remove that and in MATLAB get to put it somewhere else. So if I actually use that's a good idea, probably not in this case. So anyway, then I define lots of things like the radii. I've used the same letters to match my models. There's my density of my planets. You can see a mass divided by 4/3 pi r cubed. Pi is pi. There we go. So MATLAB has a sort of inbuilt calculator. And then I work my way through to work out the periods. So if I put a breakpoint here, actually, that might be quite good. So if I run this one, let's go for, where are we? Home, where's my run button? That's interesting. There we go. Right, if I click on run, there we go. So I've stopped there. And if I hover over these things, there is my period in seconds. And these are all my variables. Okay, so it's quite visual. You can sort of really see what's going on. And all the variables appear in this corner here. And if they're an array, like a sort of grid of things, they will appear as a sort of spreadsheet. So if I click on one, you'll kind of see the idea. So it appears in a spreadsheet, basically. So it's really nice to sort of check what's going on. Anyway, so I draw my initial setup. So if I just run at this point, there we go. So there's my sort of lurid planet. And I've generated a sort of spreadsheet of values. This is my theta values. I've got 1,000 of them, or lots of, there we go. That's a very long spreadsheet. So these are between 0 and 2 pi. And then I'm plotting various things. I set the title. And then I've got a simulation in a while loop. So basically, I've got nothing to stop it. It just keeps going forever until I quit it. And what I'm doing, I'm updating the time. I then work out the y positions of both the dropped mass and the orbiting mass. So you might look at so r cos 2 pi t over the period.
Can I interject by asking a question which is quite pertinent to this question that was asked in the chat, which is how do you select dt?
Right. Okay. So a lot of this stuff, I would sort of say, okay, what you could say, well, maybe we'll have 1,000th of the period. So I could actually define, it may be a better way of doing it, is to work out the period and say my time interval is a large number of these, or I'm going to have so many periods for my oscillator, maybe one of them, I'm going to divide into 1,000 steps. So there we go. That might be a better way of doing it. Or you could just say, well, my period is pretty long. Let's just define a time interval to be a very small fraction of that. The smaller fraction of your overall sort of time of your simulation, your simulation take longer to run because there's more steps to compute, but it will be smoother and usually more precise. Okay. But we obviously can't set it to be 0 because that would require infinite computation. We have to do an analytical solution, using calculus, etc., to do that. So there we go. So yeah, very good question. And with this is the sort of stuff we saw last week. What do we set as our time interval? So I would say in this case it's quite easy because we could basically, I could probably do it here. I could say dt is p divided by 1,000. All right. And I could put a break. In fact, I don't even need a breakpoint, but I could make that, I could sort of comment that out, save that and run it. And there we go. All right. So it's doing exactly the same thing. Okay, there we go. Good question. Right, let's save that and get out of here. All right, so next, what are we doing? Right, so okay, so in terms of, we're kind of wandering into our presentation from last year, so I'm going to sort of get a bit quicker on this one, just to sort of give you some ideas of things we can do. So a real simple one would just be to put some data of the planets into Excel, work out the periods, maybe plot it. All right, and just another little thing to note, this is our Kepler's third law that I'm sort of hovering over now. Our seconds or kilograms, is that a good unit? Well, why don't we do it relative to the Earth? So for the Earth, a year squared is 4 pi gm sun, we ignore the mass of the Earth, AU cubed. So an AU is 1.496 10 to the 11 meters, the average distance between the Earth and the sun. So if I literally divide Kepler 3, which is this for our solar system, by this expression, I've got P in years is A in AU to the power of 1.5. So the 4 pi's and the G disappear. Brilliant. So if I use the right units, often my equations look a lot simpler and give you the kind of power relationships that are the kind of important stuff. And the constants vanish. So, and there's nothing mysterious about this. I remember when I was learning sort of physics at school and university, I was always very perturbed when all my constants disappeared. And people would say, oh yeah, let's let the speed of light being 1. Well, how can it be 1? You know, so that used to fox me. So I think a better way of thinking about it, they weren't wrong, by the way, but just in terms of the language, I think if you actually talk about almost simultaneous equations and dividing them, then literally, if your period has in units of years, the years cancel. All right, so units as algebra, very, very useful idea. Okay, so there we are. So there's a nice plot of Kepler's third law for the solar system. And you can see the units are nice ones in semi-major axes and in years. All right, and you can sort of, so we look at all the sort of small planets, they're all bunched up here. So this is really a plot only for the outer planets. Right, so the first challenge in the Computational Physics Challenge of last year was to make an Excel sheet to show Kepler's third law, and the correlations you can see is extraordinarily good. So that's the first thing you might want to do. And you could easily, you can probably tell from the images here, that's in Excel. That's in years, and I'm plotting that versus this lot, and we should get a nice straight line of gradient 1. Okay, so we could do it for exoplanets too. I don't think this was in the challenge, but you can, I think that's in one of my my downloads. This is for 648 exoplanets. There are many more now. And so what I've done is I've plotted T squared versus A cubed, but we have to worry about the mass of the star itself. And sometimes the planet, if it's huge compared to the star, sorry, I mean huge, it's similar compared to the star. So it's very similar, but what I've got is this sort of ratio of the masses in solar masses. So I've got the total mass of the star and planet divided by the mass of the sun here to the -1. So it's not going to be quite the same as before. And if you plot that for all of these exoplanets, you get a pretty straight line graph. So Kepler 3 is pretty good. These green lines are the enormous error bars in the measurements for large semi-major axes and large periods. Okay, and maybe with the sort of the modern astronomy, we might expect those to be perhaps a bit smaller. Right. Okay. So the next challenge, let's go back to our ellipses. So that's our recipe book for elliptical orbits. And this bit in the second one is how we go from polar coordinates to Cartesians. So something like MATLAB or Matplotlib, it probably doesn't have a polar plotting library per se. So what you do is you create an array of angles, which is what I did last time. So say 1,000 linearly spaced angles between 0 and 2 pi. And I can, if I know what R is versus that using my equation here, I can work out the X and Y values and I can plot the orbit. And if I know where the orbits are, I can sort of create a patch. That's a sort of MATLAB term for this sort of sector here. Lots of different languages have slightly different sort of ways of doing it. But this whole figure, apart from the maths on it, is generated by MATLAB, okay, including the title. So that's a nice thing to do. And then you can start applying that for all the solar systems. So that's another MATLAB plot. There's a very, very good video called The Solar System to Scale, which I hope you've seen in your physics classes. If not, put that into YouTube. It's rather good. Some American guys drive in the Black Rock Desert. And really, you see that there's massive differences between the inners and the outer planets. Okay, so this is to scale. And if you want to look at the inner planets, then you kind of need a separate plot. So there we go. Now, the next step, you say, well, I've plotted a static model. Let's go and animate it. So in your sort of while loop, you can sort of have these sort of going round. And if I've got an animation of this, actually, I might sort of, let's just have a quick look. So astrophysics, solar system, I don't think I do. Let's just have a quick run of that. What does that do? No, that's a completely different thing. Yeah, I'll show you that another time. Orbit dynamic simulations. Let's have a look. Binary stars and planets. Nope. I'll cue it in. So I bet they've got lots of different simulations here. But sort of take my word for it. Here's a little animation. In fact, if I click on that YouTube video, that might be better. Let's not do that. I don't think we need adverts for YouTube. But take my word for it. We've got a little sort of animation going on here. Right. Okay. So we can have another one, which is now looking at it in 3 dimensions. So for most of the planets in the solar system, we're in what we call the plane of the ecliptic. So it's all basically one place. So a 2D model is perfectly fine. But for Pluto, that's not really fine at all. You can see here that the angle is quite a lot. So it is Pluto, it's about 17.5 degrees. All the others, well, Mercury's quite large, that's 3, and Venus is about 3.4, Saturn's about 2.5, and the others are less than about a degree or less, okay, relative to the plane that Earth's orbit forms. Okay, so I guess that defines the plane of the ecliptic, the Earth's orbit. So what you do is you kind of tilt the coordinate system. Again, I think you want to have a look at the maths in slow time for how you would rotate things, but that within sort of next simulation to do. All right, so this is the sort of recipe book. I've also got things like the radius of the planets, the rotation period as well. So you could even have the planets spinning around, although to scale they'd have to be much bigger than they actually are. Okay, and interestingly, some planets rotate the opposite way around. We call these a retrograde orbit, which are Uranus, Pluto, and Venus. So there we go. So there we are. So the next bits. By the way, have we got any questions? There's a little bit of a mathy thing we're going to do now. Anyone got any questions? Nope. Okay.
I think 1 or 2. I'm not quite sure. If you used Excel, for example, for starters,
Okay.
The question is, do you put in the sort of one of these complicated formulae and just get Excel to work it out, or or do you mention iteration?
Right. Okay. Excellent.
Using a simple iteration, a set of equations.
Right. So what we've got, I've got a few Excel models. Now, in some ways, I've got this because it probably looks quite busy. Because we've got everything. We've got the plots, we've got the data. So this particular one has got an iteration. So this box will be too small to see, but basically it's working out what happens next. So what I've got here is, this is Mercury. So I've got time going iterating. All right. So this would be in years. I'm working out what X, Y, velocities, accelerations do, and an exact model as well. All right. So that's how I've kind of worked these through in Excel, and I'm using that to plot a sort of inner and sort of outer solar system part. So everything's kind of in there. I've also plotted the sort of exact model, which are these ones. If you look in here, we've got a cos 2 pi times the time over the period. All right, so it's pretty much the same model that we saw for the masses going around the planet for our sort of planet plotter. So you could just do this bit, and that would be absolutely fine. In fact, that's probably one of the first orbit simulations I would do. Just literally plot the orbits themselves analytically. But you could work it out in terms of in terms of sort of an iteration as well. So I've got another little one to show you. So here we go. So if you start with, so there's another solar system model. So I think this is entirely analytic. So we've got all the data in the corner for the planets. And then we've got, see from Mercury, the range, the X, the Y, the velocities, and the speed. And if you look in this, I've got a kind of, it's a bit hard to see in Excel, but you've got this semi-major axis, 1 minus the eccentricity squared, 1 plus the eccentricity times the cos of L6, which is the angle. All right, so it's a bit harder to code up your maths. So basically, you write your maths on a piece of paper, and then you use that to work out what your formulae are, and then you use this sort of green button to replicate that down in Excel. So actually, I think this is I mean, this is the full elliptical orbit model. I would start with circular orbits. All right, that's the first thing I would do. If you think, yeah, I can do a bit better than that, I would do something like this with elliptical orbits, and you can do some fun things like look at the orbital speed versus angle. So the blue one is Mercury. That's quite intriguing, isn't it? And then you can sort of see that these aren't perfectly circular. Of course, the outer solar system, you get a much better view of the elliptical nature of it. And then we'll move on to other sort of binary systems. So let's just have a little look at other things we can do. So I think I might skip over this a little bit because there's some maths to do. But if you really are a calculus fiend, we can actually work out the rate of change of angle swept and use that to work out time. And if you sort of do that mathematics, you get the orbital, the time, in terms of angle. And this is involving an integral, which is called an elliptic integral because it's related to ellipses. And you have to do that analytically. An integral of 1 over 1 minus epsilon cos theta all squared is sadly not one that you can do. All right, so you have to do that with a computer. And what you do is you literally just divide it up into small angles and use them like a trapezium rule to do it. So here we go. So this is one of the challenges from last year. So here's, for example, a sort of function which varies in a sort of wiggly way. We're dividing those up, but not in trapeziums. We've used some quadratic equations between the points, and then we add up those areas. We can integrate a quadratic quite easily into a cubic. And if you do that, you get a really interesting rule in terms of what the y values are. So you've got y versus x, an array of data. You have 4 times the odd ones and twice the even ones, minus the sort of width of the strip, in our case will be theta, or the angle difference in theta, and you can work out what that integral is. So this is something you can code up. It's called Simpson's rule. And that means you can work out the time versus angle for different elliptical orbits pretty accurately. So if you look at Pluto, there's the New Horizons picture of Pluto, an absolutely amazing picture. Look at that. And you can sort of plot it. So this is the circular orbit, angle versus time. And then you can plot the version that you've just computed numerically, and you get a little bit of a wiggle to it. All right, so it doesn't make a huge difference. If you were to do an animated gravity sim using circular orbits, you're probably not going to use to send a spacecraft there. You'd miss it. But for the purposes of your physics education, that would be an excellent start. But if you've kind of got to that stage and you want to make it more precise, then try something like this if your calculus is good. So there we go. That might be a nice project. And this is about the MATLAB code. So again, I won't go through this, but you can sort of see we've got some commentary and other bits and bobs. Okay, so some fun stuff. Well, it's all fun, but this is might be something more particularly. Once we've got a good model of orbital motion, we can do something artistic with it. So this is a really nice thing to do. So what you do is you say, give a time interval, let's just say a month. And if you say pick a pair of planets, let's just say Venus and Earth, and you draw a line between them, a straight line between where they are. And then you go to the next month and work out where they are, draw another line. Now keep doing that for, I don't know, n orbits of the outermost planet. So I've picked 10 orbits of Earth here. And I think I've done it, not as every month, but I've done the n times the maximum orbital period over 1, 2, 3, 4. It's a rather arbitrary time constant. And what you get is amazing. What you get is something that looks like this. So, and it really plugs into the kind of numerology of the past. So there's this sort of 5-petaled relationship, a sort of factor of 5 between the Venus and Earth orbits, which you then get represented here. For Jupiter and Saturn, it's a sort of slightly distorted 3-way relationship, okay, sort of orbital resonance. So there's all sorts of pseudoscience that came about before Newton, music of the spheres, etc. But it does have some factual basis, which you can create for yourself. So this is Mercury and the Earth. I think that looks like something you'd see in a microscope, kind of virus. Uranus, Neptune is really strange. I think that's that could be on a pendant somewhere. You know, you could, maybe an enterprising member could print these onto T-shirts. Young enterprise, that kind of thing. That'd be great. This is Neptune, Pluto, and that's even weirder because, of course, it's not even the same plane. Venus, Mars looks a bit like, I'm not sure I can like that one so much. And there we go. So the final challenge of last year was to kind of go one step further, really. So So you're probably aware that Claudius Ptolemy, 100 to 170 AD, well, obviously it's the done thing that the Earth is the centre of the universe, and in fact, until kind of people like Copernicus, etc., got very brave, you kind of got burnt at the stake if you if you said otherwise. But actually, it's a perfectly valid model to have the Earth to be the centre of the universe, as long as we don't expect that to be special. Right, so from a perspective, a kind of coordinate system, that's perfectly valid, except it's really complicated, the motion of the planets, and in fact the sun about it. So the sun forms a circle about the Earth, and all the other planets form these sort of weird spirographs. So here we go. That's the, so I'll show you a few pictures. This is the outer solar system relative to Pluto. We've got the outer solar system relative to Saturn, and the inner solar system relative to the Earth. So here's some nice pictures. So this is the sort of first one you might do, and you can sort of see the Venus one, the Venusian orbit that we saw before. And Mars forms this wonderful retrograde loops. But we don't have to use the Earth. Why not use Saturn, for example? And you can see the Jupiter sort of three-part symmetry here. The other's a bit more complicated. And here's some more. So, pick one that you like the best. I quite like this one, the one with Mercury or Venus. That's really interesting. So the blue one's the Earth, which you would expect to follow the similar. There's a kind of pentagonal shape here as well. What's another nice one? Yeah, the Jupiter one is pretty good. All right, and kind of the inner solar system ones, well, they're quite a sort of long way away, so it doesn't quite look so pretty. Anyway, so lots of ideas to plot. So once you've got an orbital model and you can work out position in X and Y versus time for your orbits, and again, you could have that as a circular orbit. They wouldn't change a massive amount. You don't need to do that complex one, a tricky calculation working out time from angle that we saw earlier. That just refines this a little bit. You could create these quite quickly. So that could be a great little project for some of you to do. But you need to find a nice program to make the graphs, I think. Is that a question that's come up? All right, so we've got a few more minutes. There we are. Right, so just to sort of give a few more ideas. Well, what happens if we have more than two stars or planet? So unfortunately,
before we go on further, can we answer some questions which are pertinent in the previous bit? Okay. So question one: in the Excel spreadsheet, there were X and Y values. So are the X values the semi-major axis? The answer is no. But can you clarify what the X and Y values were?
Okay. So what we've got here, the semi-major axis are kind of the inputs to it. So in this case, I guess the distance from the sun in AU, that should be sort of down here. Okay, so that's kind of your semi-major axis. The X and Y are literally the coordinates in your system itself. So if I follow, for example, the orbit of Mars, which is the purple track here, what I've got, actually, let's do Mercury, because that's the one on my screen. So that's the little blue one. All right, so I've plotted, I don't know how many data points, quite a lot, several hundred. All right, literally, it's this whole column here. That's what I'm plotting, X versus Y as a scatter graph. This is a scatter graph. All right, but if I right-click on it and go to Select Data and go to Edit on Mercury, there's a bit of nomenclature. It says N4 to N709. Right, so that's the X values, and 04 to 0709 is that column there. All right. Any more questions? Nope. Right. Oh, yes, one more.
So, do you know what's the best way to animate Excel?
Right. Okay. Right. Okay. So I'm going to show you a little simulation. This is a bit of history, right? So this is something I wrote in 1999 when I was a university student, and I hadn't really done much programming before. And so I was set a task. I think Dr. Chung might have also been set this same task, actually. He was university a little bit later than me.
I had the same task.
You did it. So this is about interacting galaxies. Now, I have a little...
I use a different language, though.
So what I've got here, it's a bit small to see if I zoom in. Got the same kind of idea. Bit more complicated, because what we've got is circular motion of these star masses, and they're going to execute mutually circular orbits. You can make it elliptical if you like, but a circle is fine. And I've got these little masses that orbit around these ones to start off with. They don't have any interaction. Their mass is negligible, but each one of these feels the gravitational force from the blue one and the green one, right? So what you do is you kind of animate it by using something called a macro. Now, Control G used to go really quickly. It's actually going to work. And you can see this is incredibly slow. So I'm not quite sure why that is. If I click escape, it goes a bit quicker. All right. But you'll see the whole thing evolves glacially slowly. Now, there may well be, if you know a bit of Visual Basic, so if you go to click on debug, all right, you get this sort of code stuff. And what I did literally is I recorded a macro in Excel because I didn't know any programming at the time of copying stuff from one cell to another and then repeating that process. So it's really tedious. It can be done. There might be a much better way of doing this. So this took me several hours to do. All right. So this is why you would never do an animation in Excel, but it can be done. I'm not going to save that. And eventually what you do is you end up with something which looks like this. All right, so we are running a little bit like this one. So I think I'm going to cut to the chase and show you a gravity simulation. There we go, look at that. So this is what happens after, I don't know, how many simulations that? Probably 8.5, so probably about an hour later of pressing go, I get this. And then you can see this sort of exchange of masses. So what I'm going to do is I'll talk about what this a sort of binary system. And I've got a little animation here. So let's just run that, shall we? So I think it's binary stars and planet. Let's go and run that. And here we go. So I've worked out the entire orbit. And basically what's happening, these little stars are executing mutually elliptical orbits. They're slightly different masses. The period's 2.32 years. And this is a poor little planet that happens to be in this system. So it starts off orbiting this planet. But of course, it feels the strength of gravity to this one too. And the resulting orbit is not circular in the slightest, and eventually it gets ejected from the system. So you can play around with all sorts of these things. So the three-body problem is complicated. However, we can just write down Newton 2 and work out what happens next in a loop. And this is the Verlet method. It's constant acceleration motion between time steps. And our acceleration is involving Newton's second law. So again, this is something not to just to look at in slow time, but what I'm doing is I'm evaluating Newton 2. These are all vectors. And I think just to go in slow time, see if you can work out how that all works. So in general terms, we're just applying Newton 2, but remember, everything's not in the same direction. Okay, and there we go. So that's how it will all start up. Right, so this is quite a fun one to do. This is a ring orbit system. And I think it is, which one we got? It is orbit system. I think it's not this one here. Bear with me. Yeah. Where have I? Starter white dwarf. There we go. So in this simulation, what we've got is some, so this is sort of much quicker, but we've got lots of test masses orbiting. So we've got loads of circular orbits. And we've got a little sort of planet sort of working its way through. So this could be maybe a nebula or something like that. And then something bad happens when this planet reaches the end of its circular orbit. The star in the middle loses some of its mass. So see if you can see what happens. There we go. So it loses its mass, and then we get this sort of kind of shock wave of gravity. And what happens is the orbit of this one now becomes an ellipse, all right, because it's going too fast for the circular orbit. And this is what happens to the masses. So there's all sorts of fun you can have. So a nice one, if I go to a gravity sim, you can do it in 3D too. And this is the sort of default one. And this is running on my computer. I don't have a particularly fast one. And you can see I've got a whole swarm of initially circular orbits that form these sort of rings plus all sorts of other stuff. This is a bit ridiculous because I've actually set the walls, things to bounce off. So you can see the planets bouncing off the walls. So show you another one. This is perhaps a similar one. So what do we got? Let's go for the solar system. All right, and there we go. Let's go for 2D, which I think is 2. There we go. We've got a problem here that one of the masses has been injected in the simulation. Let's quit that. Let's run a silly one with unequal masses, and now the orbits are 90 degrees. I'll just restart that for you can see. All right, so if I just restart and pause, you can see, oh, it doesn't pause very much. pause W. That's there we are. I think I've set an unrealistic simulation of the masses bouncing off the walls here. But ultimately, you get these sort of tidal tails which are kind of representative of galaxies. So I've got a few pictures of this. So let's sort of whiz through. So here we are. So this is one of those sort of simulations where I've got sort of initially circular orbits. So let's just sort of look through. So we've got circular orbits of this one. And basically what happens, it sort of devours the other one here. So this is five solar masses. This one is 3. And it kind of eats them as it goes. If I've got the, I think I might have this actually. Let's go and have a look. So orbit simulations, interacting galaxies. I hope it's this one. Great. There we go. How's it done its thumb? There we are. This is a little bit clunkier. So you can see this is being worked out and calculated in real time. All right. And you see these really beautiful shapes forming. Okay. So we've got mutually, won't be quite, I think I've set it to be circular orbits. About a sort of center of mass, and these little masses feel the kind of gravitational wind, if you like, of the others, and we get these tidal tails, which is quite representative of real galaxies. I'm just going to quit that. So to sort of finish off, here's a Messier 83 galaxy. Control Alt to see that, and you can see these tidal tails. Now, to simulate this properly, you need a supercomputer, but we can get something that looks kind of similar with a desktop PC, and if you're really keen, Excel. Here's 52 random masses where I've used this Verley method. That's quite pretty. Here we are. This is sort of a random one. I'm not sure that's pretty physical, but it looks quite interesting. And just to sort of finish up, there are systems in the solar system where we do have lots of stars orbiting each other. They're probably not that close enough to interact directly, but we do have some quite eccentric elliptical orbits. So the center of all of this is thought to be Sagittarius A star, which is a supermassive black hole, about 4.2 million solar masses. And of course, recently that has been imaged directly. So I think we have about to get to 9 o'clock. So I think that's probably quite enough. There's a few other bits and bobs in this talk, if you want to have a look, such as Hubble's law. But I think if you...
Can we use this time to answer a few more questions?
I think so. Yeah, absolutely. Right. Okay. Give me the next
question. So let me read out a few. In the interacting galaxy model, did you assume all the matter in the nebula is subject to Kepler's laws?
Right. So if I go back to, I think I could probably, let's go back to this one. So in this one here, so my starting condition, all right, is I've got all the little masses are executing circular orbits about their corresponding mass. So this one here and this one here. Of course, they will have an extra velocity, which is the center of mass velocity of their kind of companion star. And those velocities are set to be circular or elliptical orbits about a common center of mass. So the red one and the blue one that you can see here, they will execute either elliptical or circular orbits. So that's completely analytical, exactly what we've been talking about already. The difference is you do it in a loop and you use Newton's second law to work out what happens next for all these little masses. There's no interaction between the green masses. There's no interaction between the purple masses, but all of them have a force which is between the red one and the blue one. What makes this interesting is as the blue one and the red one move, obviously those directions of those force vectors will change, and of course their magnitude will change too. So you've got to do it in a loop. So that's what makes this sort of really interesting. Any more questions?
Do you recommend a particular Python package for animation in Python?
Oh, so I'm not really an expert in Python. I think matplotlib doesn't quite cut the mustard, as it were. There is something called Pygame, which a number of my students have used. But I think if I recommend something, I'm sure some of you go, no, of course not, use this. So maybe some of you could get together and go onto forums and put some ideas. If you do have a look at some of the videos for the Computational Physics Challenge for last year, there were some absolutely amazing solutions for some of these problems. Some of them are really smooth indeed. Things like JavaScript, people were using C#, C++. C++ will be very fast. You might even be able to access hardware itself. But the trouble is that you might find that 99% of your effort is going into figuring out how to make your animation work. Whereas I think 99% of your effort should be about getting your physics right and getting all the things written out in simple code. So even if it looks a little bit amateurish, like my graphics do, get something to work fairly quickly, and start in Excel, or if you're familiar with Python, do a little bit, get an orbit done, and then incrementally build up your simulations. Otherwise, I think you'll get thwarted too easily. So build up something that gives you some sense of satisfaction, and then make that a project, stick it in a tin, as it were, and then ask yourself, okay, how could I then make that thing better that has already worked? Any more? We've probably got time for maybe one more question.
So my point of view is that there are lots of different libraries that output graphics. You need to find the one that fits best with what you want to do. I've used VPython, Visual Python, where some of the graphics comes out quite nicely. Pygame also works for making games, unsurprisingly, and you can use those graphics primitives to help you. But I would say, without knowing precisely what you want to do in terms of simulation, it's unclear which one to recommend. And the packages change so quickly, so you should Google, look at what the latest is for what you want to do.
Yeah, so I'll just run that one more time. I think to make it a bit faster, hopefully.
And Manum is an example of a very hard to use package. It was written by Grant Sanderson, which he's brilliant. Unfortunately, he hasn't written particularly good documentation, so that if you're not Grant Sanderson, it's actually a bit hard to use.
Yes. So, but basically, if you write something out on a piece of paper, you define your model. Do everything on paper. You would never ever start with your computer program. So imagine you were trying to teach your friends how to define the orbits versus the X and Y positions versus time of the red and the blue stars here. Okay, and then write down something similar in a loop for all the different masses that are orbiting initially circular. Then you use that armed with your computer program to try and code it up. And there we go. We can sort of see this looks quite realistic. You've got these big tidal tails, and you've got this sort of mass transfer that's happening between these two galaxies. Okay, so I think I will probably, unless there's any more questions, I think we'll probably.
Let me just ask one practical question, and if there are any questions, leave them for next time or send us an email. The question is, for the actual challenge, I think in the previous webinar you said there were bronze, silver, and gold challenges. Can we enter for a multiple of these?
Right. Okay. So the way it works is that you, I don't know if I could sort of just quickly bring up one of these. So if I go back, I think it was sort of earlier. So there we go. So challenge number 1 would be rated bronze. Okay. So the idea, there's about 10 challenges, and they'll have a bronze, silver, and gold rating. So the idea is that we kind of look about what you've done, and you put your solutions as a YouTube video. And if you say, like, well, I've just done the bronze ones, I've only done the bronze ones, then you'll get a bronze. The silver ones, you have to have done quite a few of these, maybe had a go at some of the gold stuff. So to get silver, you really need to have done a little bit of computer programming. Okay, so you can't really get a gold or a silver if you just use Excel. And if you want to get a gold, then we've got some harder problems, like, for example, the animation here, 3D, maybe you've done the sort of maths bit here for this one, you've made these spirograph pictures. If you've had a really good attempt at the gold problems, then that's the kind of thing we're looking for. And there's also a competition as well. If you are really super keen, the top 5 will get that's quite hard to do. We had some amazing stuff last year, but we've got some extension challenges. So people made apps, they made websites, they wrote papers. So it's as much as you get into, really. This is the project's released at Easter, and let's find a pretty one. There we go. So the project's released at Easter, and you've got until the end of August to do it. You can do it in pairs. That's plenty of time to do something really awesome. That's not an examination. So this is quite different from a lot of the other sort of challenges that you will face, both at A level and for BFO. So there we are. That's the kind of idea. So any more before we go?
I think we should leave it there.
Yeah, brilliant. Okay, thank you very much, everybody, and we'll see you next week. Thank you very much.
Okay, thank you, Dr. French.
Let's come out of that. There we go.